Hello, everyone, and welcome to our presentation today. We would like to welcome the folks from Gigaspaces, and specifically Nadi Shalom, who is our presenter today. Nadi is the CTO and founder of Gigaspaces, and has 10 years of experience with distributed technology and architecture, specifically with cloud computing, SOA, and Grid. He is a software visionary and industry leader, and is a frequent speaker at industry conferences. Like all of our presentations, we invite everybody to ask questions throughout the webinar using the Q&A panel that is available in your WebEx client. And if you have any problems throughout it, please feel free to private message those to the host. And without further ado, I'd like to get things started. And here's Nadi.
Thank you very much. The topic of today is, as we said, is the Nosql Alternatives. It's a pretty interesting topic because I think it covers almost 20 years of industry background around databases, database scaling, and the alternative approaches to that. I'm hoping today to cover most of the principles. Obviously, when we're going broad, that means that I won't be able to dive too deeply on the topics, but therefore the main purpose is really to give a glance view of what's going on there, what stands behind Nosql, what are the common principles, what are the common terminology, and what's out there. I'll start with a quick introduction to Gigaspaces, and then I'll switch to a call that will basically help me to understand who is on the call and at what level should I talk during the discussion itself. So Gigaspaces, the vision behind what we're basically trying to do in the past 10 years is trying to address two things. One is solve a lot of the distributed programming problems, which means scalability, consistency, failovers, all those hard issues. But on the other hand, we want to make it simple as if you're writing to a single machine. And that's kind of the two folds of this vision is really what we're trying to do in the past 10 years. The product itself is named up and is being used in leading industry. It's generally speaking, it's a distributed application server that includes messaging and data capabilities, and is mainly used in event-driven and transaction processing application. You can see some of the list of the customers that are using it. Most of them are in the financial industry running today. A lot of them are in production. And we're seeing more coming from e-commerce industry, social networks, and other industries. That's pretty much going to be the only slide that I'm going to talk about Gigaspaces, and with that, I'll switch to the first call.
So everyone, we have opened up a quick poll that Gigaspaces was wondering what brought you to this webinar. So you should see down in one of the panels of your WebEx client several choices that you can answer, and we would appreciate you taking the time to fill these out. Okay, so we're going to close the poll here in just a second. And it looks like from the results of this, it looks like most of you are looking to understand what exactly is the NoSQL movement and how that can help you change your current data persistence system. So, Nadi, if you'd like to continue.
Thanks very much. And thank you all for participating in that poll, because that really helps me to understand where to focus on the presentation. The agenda for today will be broken down into mainly two parts. It's four parts, but it's mainly two parts. One of them is going through a quick overview of how databases and clustering are being used today and what are the limitations, and why we're even talking about Nosql in the first place. And the second part, starting from the Nosql Alternatives, would look for the different approaches to database scaling that exist out there, both in memory and in file system-based solutions. We'll talk about the common principle, the query models, and towards the end, we'll try to kind of marry the two, the existing world and that new world, and see if we can bridge them and what are the strategies to marry the two. I'll start with the existing world and go through a very quick overview of how typical scaling approaches looks like. The first one is what I would call the share mapping approach, where we basically, the share mapping really means that it's not that our application don't have data, it just means that the application tier that is outlined here don't contain state, and it basically relies on the actual database to do and manage all the state of our application. In that scenario, the scaling is really assumed to be mostly read, and therefore the scaling challenge is more concurrent users trying to read the same data. And therefore, the way we normally work through that is when the number of clients grows, we'll basically add more web servers, and we'll scale up the database. Scale up meaning that we'll either buy bigger hardware or add more CPUs to our hardware if that's capable. And by adding more web servers, we basically balance the load between those web servers to the database. So assuming it's a read-mostly application, we can balance most of the read load through that. Obviously, that has a limit, and if all of them are going to do a lot of access to are going to end up doing a lot of access to the database, then the database is going to hit a wall, and we'll need to solve that. And therefore, one of the solutions for database scaling was coming through an architecture called Oracle RAC, or a RAC architecture, which is a real application cluster. In that approach, what we're basically doing is we're trying mostly to understand database high availability by sharing storage. So as you can see in this picture, we have two nodes. One of them is acting as a primary, the other one is acting as a backup. The application is supposedly seeing both of them as if they are one database. And through the share disk, if one of them failed, the state of the database is stored in that shared storage, and we can basically see that in the data, and when the application switches, we can actually switch to that node as well. So the limitation of that approach is that it's very expensive. We have a lot of hardware dependency in our approach. We need to set up a fairly complex environment, and as you can see, it does addresses the high availability of the application, but it doesn't address as well the scaling in this type of architecture. I do see a few questions coming up. I'll address them as we start with the next call, so I'll wait with that a little bit. The other approach, and that's actually a slide that I borrowed from one of our customers, eBay, in the Netherlands, which talks about traditional database scaling through a master-slave environment. A master-slave configuration means that all updates goes to a master. In this case, it's called the main master, and there is a backup master like in the previous slide. But to address the read scalability, we're replicating every update into a pool of other databases, and when there are reads, the reads can be load balanced between all of those slaves. They are slaves because they basically use only for reads, and they are dependent on the traffic coming from there. As soon as we're starting to see more traffic coming into our system, obviously that means that every update needs to go in this direction, and that means that our system could be saturated and pretty busy just doing those writes and updates, and therefore it's good for scaling on read operation. It's not it doesn't scale well on write operation. It's also not that trivial to write applications, so that the write will go to one node and read will go to another, so it's fairly complex to maintain an application that is written in that approach. Now, that kind of covers the existing world. And now let's see why we're even sitting here and discussing all that topic. Now, when I sat and tried to kind of view the different trends that lead us to discuss a lot of those things, obviously social networks were one of the first items that pops up. social networks really changes a lot of the behavior, the web behavior, and the web traffic that we've been experiencing. I took here the picture here shows the traffic trend on Twitter. What's interesting is that two things happen. One, if the assumption was that web applications were mostly read-only or read-mostly, with Facebook of the world and with Twitter of the world, that changes. It becomes a read-write scenario. The other thing is we could see in terms of traffic, the traffic itself tends to be very viral. The interesting point is the difference between the peaks and valleys of the load. As you could see, the size of the difference that we can see between the peak and the valley grows quite substantially. So if we try to size the application, or basically say how much servers we need to deal with the peak load, we'll end up doing or provisioning a lot of machines just to serve that peak load, where in average, as you can see, we don't really need all that. So the more the differences between the peak and the average, and the more questions, the more we'll need to provision, and the less utilized will be our system. The other part that I wanted to bring is software as a service. I'll touch on that very quickly. I think it speaks for itself. We're moving from a world where a lot of applications were delivered on-site and to a single customer, and now it's moving to a web and basically needs to serve all customers through a single quote-unquote instance of the application, which obviously changes a lot of the behavior in terms of load. And the last piece, which is, in my view, the most interesting one, is the economy meltdown. A lot of people were able to solve a lot of their scaling problem by saying that they can, because no one was fired for buying IBM or Oracle, or they could throw more hardware into the problem. That statement, of those statements, doesn't hold anymore. I usually always add to that those that will be able to solve those problems without putting a lot of hardware, and we know that there is an option for that, will actually can turn up into a career path. So that is the third item. The fourth item is something that I'm going to cover in the next two slides, is really about the current assumption that led to the way current applications are built today. So our diff is safe. This is the core assumption, but really if you look at real data statistics, you'll see that disk failures are actually failing significantly higher than estimated. The reason why is fairly simple. Most of the estimation was based on some heuristics, but in reality, if you measure that in 10 years, you'll see a totally different numbers, which basically means that the heuristics algorithm wasn't that accurate. The other thing that was interesting in that research is that there was no correlation between failure and disk size, meaning that small disk and very high-end disk, remember the world putting more hardware to the problem? So putting more hardware to the problem, especially in disk size, wasn't that successful from a failure perspective. And the last piece, which I think most people would find surprising, is the fact that we usually assume that temperature will be one of the main codes for disk failures, but actually if you look at that graph that was taken from a 10 years data center statistics, we'll see that most of the disk failure happened when the temperature was fairly low. And that really tells us that a lot of the disk failures are fairly statistics and are not really related to any hardware or configuration, and a smaller disk gave like a very high-end disk. And we're not safe with disks as we think we could be. The other piece that is interesting is memory itself. A lot of people would assume that memory is expensive and not reliable, but most people measure the cost per RAM inaccurately, because what we neglect is the throughput. There is a direct impact of the cost of our disk if we add the throughput, meaning the time it takes us to actually read the data. And if we apply that based on a research done by Stanford University recently, the actual cost of memory could be hundreds of thousands times more efficient in terms of cost than a traditional disk-based solution. The other interesting fact is the capacity. Most people would say that you wouldn't be able to store your entire data in memory. But things have changed. Today we're at a point where we're reaching the point where we can have a lot of memory available at a much lower cost. So in that case, I will try to speak louder. I see people pointing to that. I'll get, hopefully that sounds better now. So what you could see is that two examples are taken from that paper from Stanford University, which try to measure a real scenarios, fairly high-end scenarios, both on online retailer and airline reservation. And as you can see, the numbers that we're getting to store that data is not that big. It's actually 4 tera, and something that we can get with fairly easily with today available memory. Speaking about today available memory, this is a benchmark that we've done with Cisco UCS, which is one of the machines that was really designed for a lot of those systems. The interesting piece here is that the system itself, the machine, the hardware, can come up with 380 gigs of memory per blade, per instance. Imagine that. So storing a terabyte of data would only need less than 4 blades, 1 chassis. So we can really store a huge amount of data today into that type of environment. So the other thing that I wanted to show in this is that we can also store a lot of data even in a single process. So that's kind of, I think, gets me to the next section, and we have the next poll on that, and this is where I'm going to answer the other question here. So while you answer the next poll. Okay. So the first question is from David Saxon, and he's talking about the financial industry and how is the NoSQL compliance. That will require talking about specifically on specific implementation. There is no generic answer to that because it's very application specific, and I don't think that in this specific case I can actually point to one that are compliant or not. The other question is, Summer, does this have any relationship to Link? The Link, for those who are not familiar with, is related to a technology by Microsoft. And it's basically a mapping layer that enables you to plug in different data sources. It's not directly related to Link. I will talk about JPA, and you'll see some of the relationships to Link when I talk about JPA, and therefore there is no direct relationship to Link in that specific case. There is other question from David about the availability of .NET and C# wrappers. I'm not covering specific language in this talk, but I'm sure there are .NET and C# wrapper. I was actually talking to a company yesterday that are doing just that. I'll talk about Google App Engine again, and the point where we'll talk about JPA, I'll remember to mention that. So David, if I forget that, just bring that up again. Okay, how are we doing with the poll?
We're closing the poll right now. There's 15 seconds remaining.
Okay.
And I just wanted to let everyone know, everyone who's having some issues with the audio quality or the sound level, we are working on that. I know that Nadi has tried to speak up a little bit. If you continue to have problems, please feel free to private message D-Zone, and we'll see if there's anything that we can do about it.
Okay, sure.
The poll is closed. Most people have no answer to this one, and I believe that means they're just looking to find out what is the NoSQL movement and how it might be able to help them.
Okay, thanks very much.
20% of the people are interested in a need to achieve dynamic scalability. So,
okay,
I believe
I'll actually planning to put more emphasis on that during the next coming slides. So this is where I'm actually getting. So we talked about the reasons why we're even talking about Nosql Alternatives. We went through the database scaling, the existing database scaling alternatives, and how they're doing their job today, and what are the limits with their solution. The movement that is coming up is really coming from those notions, the ability to make scaling a first-class citizen. And one way in which I differentiate between the two groups, the Nosql and the traditional relational model, is scale first versus scale after. So the traditional relational models are basically categorized as scale after, meaning that you want to get functionality, consistency, and all those type of things first. And basically that means that you worry about scalability, and you would be even willing to pay the cost for that later on, versus the other group that is looking for scaling first and is willing to compromise on functionality. The group that I listed here can be split into two main categories, one of them that is file-based and the other one is memory-based. Obviously, the big names are Amazon, Google, and Facebook. Also, LinkedIn came up with a database that is called Voldemort. Facebook came with a key value store that is called Cassandra. I'll touch on that later on. Google has their big table for a long time, and Amazon has its Dynamo. Obviously, on the memory side, we'll see Gigaspaces, Gemstone, StreamScale, InfiniSpan, and Terracotta with EHCache and Oracle Coherence. So the interesting thing is that a lot of those implementations are out there, like Google Bigtable and Amazon SimpleDB, as well as on the memory side, Gigaspaces and Coherence are out there for a long time, for roughly 10 years. So we're not really talking about necessarily completely new technologies, completely new greenfield type of approach. We're talking about a lot of mature technology, and that, if anything, the market came to a point where it actually needs those things in a much broader aspect than it needed them before. So a lot of the scalability problems were a niche problem before, and now they became a much broader and need a much more mainstream need. Another point that I wanted to clarify on that is why I didn't include the Memcached in that list. So Memcached, for those who are not familiar, is a memory daemon. It's basically a process that you could run, and then you could have a direct IP. It provides some sort of a protocol that enables you to communicate with them, and there are different clients that were implemented on top of that protocol that can be running on different language, whether it's Java, .NET, but also PHP, and another layer of the stack. It's very popular in a lot of the implementation, and is being used to basically store a lot of the data and help us to deal with some of the database scalability that I mentioned earlier. NoSQL really tries to make scaling of the data and provide an alternative approach to a database, versus my Memcached, which is basically an optimization to existing database, meaning that it doesn't really provide a system of records with reliability and with consistency and a lot of things that are actually missing from Memcached to be categorized as part of those lists. And therefore, I felt that it's not something that I could put on the same list as Bigtable and Dynamo, as well as Gigaspaces and Coherence. So, what are the common principles? I listed the file-based, and I listed the memory-based. But really, if you look at that from a broad view, you would see that most of them have a lot of commonality. There is also differences, but there is a lot of commonality, and I want to focus first on the commonality, and in some areas we'll talk about some of the differences. Things that I'm not going to cover is things like transactional support, which is another interesting area. I'm just not going to be able to cover that. So the main thing that you'll see, and I'm going to talk about that, we discussed earlier the failure scenario of disk, where in NoSQL the assumption is failure cannot be avoided. It is inevitable, and therefore we'll have to design our system to deal with failure. The other thing is that we'll need to scale by not just by adding more CPUs to a single machine and basically buying more expensive hardware, but by actually using commodity resources and spreading the load across multiple nodes. We'll also assume that reliability will be maintained by replicating the data, and we're not going to rely on syncing everything to disk to maintain reliability. We'll talk more about that later on. The other thing that we'll do as we'll look at is we'll try to ease some of the requirements that we currently have in terms of consistency, availability, and partition failure, because what we'll see is that trying to cover all of them will cost at one aspect. So we'll try to see how we can cover them, where are the areas where we can compromise, and what is the benefit of compromising them. So with that, I actually borrowed that from a close friend named Jason from Amazon. I really recommend looking at his blog and his presentation. He's working at Amazon as an architect that is running the S3. And he, in his presentation, discussed a lot of the things on how they develop and how they run and maintain S3 as a storage, and how they manage to maintain the availability of that service, which is a fairly large-scale service. I think we'll all agree on that. Those are the main bullets from summary of his presentation. I'll try to touch on that fairly quickly. The first one is what I mentioned earlier, the fact that rather than trying to use expensive hardware and rely on that to solve your problems, you actually need to program your application and design your application with the mindset that failure will happen. And failure is not just will happen, it's inevitable. And you see in the diagram here that failures are sometimes human failures, like someone throwing away a complete rack, and who knows what's going to happen to that rack when you bring it back to the data center. What screwdrivers were actually got stuck in the way, and what's going to make it broken again. The other thing is the code for elasticity. If you want to make your application robust, you need to be able to deal with massive failures or multiple node failures. And if you design your application for elasticity, that means that you could tolerate that failure. That even if few nodes will fail, or even if a complete data center will fail, you have the tolerance in your architecture, in your application, to move to other machines and continue to work from there. Versus if you rely on that to be robust and never fail. Obviously, monitoring and exploration will enable you to continuously optimize the system and design, or at least prevent failure before they happen. So that becomes also an important part. I'm not going to touch too much into that. I think, again, those points speak for themselves. The other principle is partitioning. For those who are not familiar with the concept of partitioning, partitioning basically means that rather than storing all the data in one store, one big server, one big database, we can partition it. So one common way is to partition it based on the user ID. So I took here a Twitter example in this case, and basically what we see is users that are sending tweets. In this case, the way we scale them is by sending each tweet, every tweet that we send will go to a different partition. So if I'm Nati, that means that I'll go here, and if you're someone else, like David Sexton here, you'll go to here probably, and things of that line. And by spreading the load based on that key, we can spread the data, but also the load, the traffic across those partitions. And basically, that means that we can add more resources to our application, and because we can spread both the data and the load, we can actually get the actual sum of all the resources as our big servers. That gives us two things. One of them is the actual compute resources of each of the nodes that could be compiled into one big node, as if it was one big node. The other thing is that it will enable us to also use commodity resources, and use commodity resources as a mean to basically create a big an equivalent of a big server. The other thing that is important in partitioning is because we're actually spreading the data between multiple nodes compared to a centralized database model. Think about it as a table. We're actually splitting the table into multiple smaller tables. What happens is that we reduce the contention of the table. A table lock is now spread across those partitions, meaning that we're much more parallelized and concurrent, and we can also leverage the actual CPU power and the actual memory power of each of the partitions. Now let's see how we deal with reliability in that scenario. Now remember that we can't really, and we don't want to assume that our data is reliable just because we store it at a specific storage system or into a specific file system. Because if we do that, then we'll be as strong as that weak link, and that link can be fairly weak. Instead, the common model by which we handle failure is through replication. Basically, that means that we'll maintain more than one copy of our data. If we maintain more than one copy of the data, if something fails, we can basically alternate the request of that user to its replica. In reality, it doesn't really mean that the replica will be a passive node. We actually assemble the partitioning with the backups on the same machine. and make sure that replicas and backups and primaries are not running on the same machine. There is one question that I do want to touch here again from David Sexton about transactional. Partitioning will make transaction more complex in this specific scenario, and therefore what you're trying to do is not to do the thing that you've done in a centralized model, like using two-phase commit, or trying to make a transaction that will span between those multiple partitions in the same transaction. That is something that you want to avoid. The reason why you want to avoid that is obviously if we do have a transaction that spans between them in one transaction, what will happen is that we're not really going to leverage the fact that we spread the load, because right now we actually made all the partitions dependent on one another for that single request. What we really want to do is break a big transaction into a smaller transaction. There was an interesting write-up of Pat Helland that was actually writing about it, and build a smaller workflow in each partition where we can succeed or fail within the scope of the partition, and at least we'll have a consistent state, and we'll rework on that failure from a consistent state. That means that if we fail, we'll retry, but at least we'll never be at an inconsistent state. So it does require a change in the way we handle transaction, the way we handle consistency, and that's the main idea here. Okay. Here's another question here from Marianne. Since I can't really hear, are the partitions controlled by gigaspaces? In our specific implementation, the answer is yes. Cassandra does the same thing, and all the alternatives are basically based on that. That's why I call it common principle. Each one of them is doing a slightly different model, but that's generally the idea. Okay, the other thing here is the consistency and availability. If you remember, I mentioned earlier that one of the things that we want to address is, unlike the previous system where everything will have to be consistent and therefore we're paying a lot of cost in terms of performance and scaling, in this case we wanted to say that in some cases we would be willing to ease some of those requirements. We would be able to say we can manage the consistency in our application code, and in that case we'll get much better performance. A scenario in which we'll get to that point will be, for example, when we're using asynchronous replication. So if we do need to use replication for availability, if everything will need to be synchronously replicated, we'll pay the cost in terms of performance because our client is going to be blocked until the data is going to be spread by multiple nodes. We want to avoid that in some cases. But as soon as we start to move into that asynchronous mode, we can get into inconsistency. Inconsistency can happen, for example, if I'm writing to one node and that goes and doing asynchronous replication to another node, what happens if I do a write to that node and then a read from that other node? I can actually read an older version of the data, and that can get to an inconsistent result. There are different algorithms that a lot of those file-based solutions we're trying to deal with to address a lot of those consistency. One of the common one is conflict resolution through versioning. So we know which version we actually wrote, and if we're seeing that the data that we're reading is an older version than the one that's written, we can actually consolidate that with a newer version and throw the older version. And also we can do the same thing with replication. If we're actually seeing that someone else updated our same data with an older version, we'll ignore that. So it's a much more complex issue to discuss right now, but that's the general idea and principle, and that's why we're having that. So the source of all that is when we start to move to asynchronous replication, we'll start to deal with consistency issue, and there is no very simple solution for consistency beyond the one that I mentioned, and there is a cost associated with dealing with consistency. For example, some of the things that you'll see with Cassandra is that in some cases the read is even more costly than write because it will actually try to read from multiple partitions at the same time and get the right version, and therefore sometimes the reads become slower than the writes, which is an interesting trend compared to the one that we're used to. In gigaspaces we handle that differently. I'll talk about that in a minute. Another approach, which is more strong consistency. Strong consistency really means that we're relying on synchronous replication. That really means that performance will pay the extra cost for synchronous replication, but will have a very high degree of consistency, and that will make our application simple. There is a question here: how is that configured with gigaspaces to switch between async and sync modes? The answer is that it's very easily configurable. I don't have the actual reference to show you that right now, but if you look at the wiki pages, you'll find it very easily. It's just a configuration option, and then you could specify, one, if it's synchronous or not, and if it's asynchronous, you could also specify the time in which it will synchronize and the batch size, meaning that how many events will be pending in the queue, and one of those criteria will trigger a replication, and that's usually how you manage asynchronous replication with gigaspaces. Another common pattern is really to combine the two. This is a fairly common deployment with a lot of the gigaspaces deployments, where in order to maintain consistency, what we basically do is the in-memory piece is kept synchronously replicated, and that's how we get consistency. The application only interacts with the in-memory partition, and therefore it doesn't really experience any inconsistency issue. But we're using asynchronous replication to the actual underlying database to keep the data in sync with the actual data itself. We call that a mirror service. In that case, we kind of get the best of both worlds, assuming that replication to another memory is not that as expensive as replication to another database. We can actually get a fairly good degree of balance between performance and consistency, and that actually makes things much simpler. The question here from Marianne is whether asynchronous replication is guaranteed to be executed. That's a very good question. When we're doing that link is asynchronous. And the question usually comes out, what happens when one of the instances here, for example, I didn't do the synchronization to the database, and this node failed, what will happen? Will I lose the data here, and this one will continue, and then the database will be stored in it will get into inconsistent state? The answer is no. What will happen is that is synchronous link here also synchronize the do log, as we call it, and therefore when that node switches and take ownership, it will actually continue from the exact point as this node, and therefore we wouldn't lose any of the data, even if it's asynchronous. We call it lateral asynchronous replication. There's a lot of questions here. I obviously won't be able to answer all of them because then we'll skip the entire time that we have for that. So I'll continue, and then I'll try to pick up some of those questions later on. The other interesting piece, and I'm going to go through several slides around that, is the dynamic partition, dynamic data scaling. This is one of the hardest problem that you'll see in most of the data solutions out there, and there's basically two approaches. One approach is called logical partitions. Logical partition means that the number of partitions at each point of time is fixed. Usually we'll put a very high number, like 1,000 partitions. It doesn't mean, in this case, and that's the reason why it's called logical partition, doesn't mean that we have 1,000 machines. Partition is just, think about it as a hash table in our memory. So we have a lot of those small hash tables available for us, and then when we want to scale, all we do is spread those small hash tables between the machines. So at any point of time, the number of hash tables that we'll have is going to be fixed, but they're going to be spread differently based on the available machine. So in one case, we'll have 500 hash tables, small hash tables in one machine, and another 500 in another one. If we add another third machine, we'll basically make that 300, 330 in each machine. And if we'll have 4, we'll have 250, etc., etc. Consistent hashing is a different model. This is the model. So logical partition is the model by which most of the in-memory alternatives are based on, including gigaspaces. The main advantage of that is that it's fairly simple algorithm, very simple to maintain, and it's very consistent and predictable and deterministic. Consistent hashing is trying to rebalance the data every time that we add or try to add more capacity. It's more flexible because we can change the number of partitions on the fly. I do apologize about the spelling on the Voldemort here. But the consistent hashing tries to basically say that if we add another partition, we'll repartition the data between the available nodes that are closest to that new partition. So rather than trying to repartition the entire data and stop the world, the consistent hashing tries to do repartitioning without stopping the world or without complete repartitioning of the entire by repartitioning of a smaller group of our cluster. In that case, we can minimize the overhead of repartitioning. So again, the advantage of that is that it's more flexible. The disadvantage is that the actual overhead of adding a new instance is going to be something that is noticeable. It's less deterministic. And the algorithm itself is much more complex. Okay. So let's see how the logical partition really works. In this case, I'm showing how we do that in gigaspaces. It's not that different with other in-memory solutions. Basically, what we could see here is a number of servers. Right now, they are empty. The first thing that we do is we call our API to create the data service. That basically will provision the data services based on the available machine that are out there in the network. As you could see, it will actually provision more instances than the available machine. Now, when we'll add a new machine into the system or when a machine will fail, what will happen is the failed nodes will be automatically provisioned into that new machine. And when they move into that new machine, you'll see that, for example, only the backups actually move to that new machine. So what we don't want is that we don't want to have a machine with only backups and a machine with only primaries. So instead, what the system will do automatically is will relocate some of the partitioning into the backups and rebalance the system. We call that process rebalancing. The interesting thing is that it all happens while the system is running behind the scenes. So what we could see here is a simple scenario of failover and how the system healed itself by the fact that we can actually move instances into that new machine. The other scenario is adding more capacity, not failure. And in that case, for example, let's say that we hit a memory threshold and we don't have enough capacity in our machines. In that case, we immediately added a new machine, and by adding a new machine, we can actually spread the partition into that new machine. And by spreading those partitions into that new machine, what we basically get is more capacity. The additional memory capacity of those new machines is now added to our pool. So that kind of shows you how failure and how logical partition really happens in this type of dynamic scaling world. I will take one more question here. There is a question here from Monis Iqbal about whether it's equivalent to Teradata, but with emphasis on OLTP. I would say a general statement to that, a lot of the principles are not really new. I mean, if you look at that, you'll actually find a lot of the algorithms implemented in mainframes. A lot of those principles are implemented even on storage networks, on storage disks. The difference here is the level by which we apply that and the level of flexibility that we have. So the fact that we can use commodity resources, the fact that we can take advantage of distributed system and apply those same algorithms in those environments is the thing that is interesting here. The fact that we can actually take advantage of memory resources and apply those same principles into memory resources is the interesting thing here, and that is the main difference. The algorithms themselves are actually based on a lot of things that actually happened and written years ago. One of the points that I mentioned on Twitter last night was a comment by Jim Barry that was actually published on 1985 about the difference between disk and memory. So a lot of those, and what he basically measured is that even 1% of overhead of access between memory and disk could lead to tenfold performance degradation when we reach that point. So this was written in '85 when he was writing or working on Tandem, which basically comes back to Moni's comment here. It's not a new thing. It's not a new algorithm. A lot of those things happened in supercomputers. A lot of those algorithms were existing in supercomputers. We're basically applying them in more commodity resources and in much larger scale. This brings me to the next topic, one of my favorite topic here, the query support. If there is an area where most of the alternatives that I mentioned early in the beginning that is very, very different between one implementation and the other is the query support. You'll see that, and I try to at least put the terminology behind those query support so that you know what we're talking about. The first one is the key value store. This is like a hash table. And basically what that means is that we can store and retrieve data based on key. The reason why that is very common with a lot of those Nosql alternatives is that it's a very simple model to scale. The other model is coming from a search engine model, which is called document model. A document model is kind of a schema-less model. Schema-less means that all the data is basically, if you like, are stored in a single table. And what we basically do is decorate each item with values and index those values. And then we can match by values rather than by table type and field type and field name. And by doing that, we can actually have a schema-less approach. And that approach is very applicable for document models, where in documents we want to be able to add fields and index on different fields based on the actual content, and want to be flexible on adding those fields. We don't want to be strict like we would do in a table format that is very, very strict. And some of the names that I mentioned are actually based on that. It's becoming more and more popular as we move to social networks. As you could imagine, that type of matching becomes more popular. The other one is SQLite. In SQLite, we're actually trying to marry the two worlds. I'll touch more on that when I'll talk about JPA. What we basically want to do is leverage the scaling of the key value store, but be able to run similar type of syntax to the queries that we were used to in SQL, simply because SQL as a language, as a query language, is a fairly good language, and if we don't use the bad part of that, it's fairly good. There is a lot of good syntax there that makes at least a lot of knowledge that people have around that syntax. What we do want to do is actually use the part of SQL that can be easily scalable, easily partitioned, I would say. And that's why I said use a partition of SQL syntax, and in most cases you wouldn't see a full implementation of that. The other part of that is aggregation. Once we partition the data, the main question is how do we actually run, let's say, a query like a sum on an average, which is aggregated, something that will need to go across the partition. For that, what we have is something that is called MapReduce that I'm going to show in the next slide, and then I'm going to touch on the questions that I see from Andre and from Bill Schott, etc. So a MapReduce looks something like that. This is our Twitter application. So imagine that I'm trying to read all the tweets of all the people that I follow. And if you remember, we partition the data in our tweets based on the actual user. So this means that would be user 1, this would be user 2, and this would be user 3. What we normally do in MapReduce is execute a parallel query that will go through all the nodes. And in that case, we can actually retrieve the data from all the nodes as if it was one big node. And that's how we basically execute an aggregated query. You can see how that is done in Gigaspaces. We have two modes of API to execute that. One is called read multiple, which basically is like a select in SQL. And with that, what we do is we create a template or an SQL query, in this case with the user ID, and we can actually get that request could go to one partition or to multiple partitions based on the value that we will provide it. So, for example, we can provide a list of user ID. In that case, it will do a hash modulo and will go to this node and this node, if those were the one that matches. Or if we put a null value, which basically say, give me all the content of all the users, it will actually be a parallel query that will go to all the nodes and we bring the data into those into our clients. Again, the clients only see a single read operation, and the actual parallelization of that query happens behind the scenes. It doesn't really see that. The other API is called executors. In that case, what we basically do is we push code from our client into our servers, and then we execute that in each server. So this is the equivalent of a store procedure. The difference is that it's a dynamic store procedure. We can actually push the code dynamically into the servers. The servers could be running, and we could use that model to introduce new, more sophisticated queries that would be actually written on either Java or .NET, or if we're used to dynamic languages, we can actually execute Groovy and some other dynamic languages in the same fashion. The fact that we can actually push code into the data is a very powerful model that enables us to do a lot of complex queries, much more than we could even do in the traditional databases, and save a lot of the latency. So we can actually push here a lot of complex semantics that is not even covered within the SQL semantics. So let me try and answer a few questions here. I'll take it from the bottom, so I apologize for those who even sent a question before. Could any NoSQL system calculate a query complexity, like SQL applied in Oracle? I'm not familiar with that. I would say that the way in which you could do query complexity, or I would say the way you could do complex query, not query complexity, or calculate query complexity, is in the model that I just mentioned. I'm not familiar with any of the alternatives that are actually measuring query complexity like you would do in Oracle. In some cases, when we're going from a centralized model to a distributed model, a lot of the optimizers are actually becoming negative inhibitors and not positive inhibitors, because a lot of those optimizations are assuming that the data resides in the same node. So a lot of those optimizations doesn't even apply here. So a lot of the things is something that you'll need to move away from. Bill Short is making an interesting question here. Our major application cannot be unipartitioned, meaning that not all tables would share the same partition ID, like your Twitter example. How would your solution handle a mix of partition and non-partition table? I think I touched on that with the MapReduce. And the Twitter example is actually a very good example for that. The key here, I mean, what you don't want to get is to the point where all your queries will need to go to all the nodes at the same time, because then you may reach into a scalability problem here. The way I try to deal with the scalability problem here is by pushing that query into one of the partitions. So at least, let's say that if I have here a lot of clients, I'm actually using a delegation model here. Rather than having each of those clients doing something like this, what I did here is a delegation where I send a request to one of the services here, and it instead did that. I'm sorry about the sketcher. I'm sure you understand everything here, like I do. But I hope you got the picture. If not, we can take it offline. It's a fairly complex topic to discuss, so I'm not sure everyone will follow on that. Let's see if I can take another question here. I'll skip that question from Monis. I do apologize about that. I will get to that in later on if I'll have time. This is the last piece of the presentation. After that, we'll have another call before the summary. The actual point here that I wanted to mention is, okay, we understand the reasons why we're even talking about those alternatives. We understand that scaling is probably one of the main drivers. We understand that scaling is done through partitioning, and partitioning and distribution of the data itself comes with different flavors, which basically forces us to think differently in how we manage our data, regardless of the implementation, whether it's GigaSpaces, whether it's Oracle, or whether it's anyone else. And the main question that usually people ask themselves is, how do I'm currently used to the current world. You right now presenting a completely new world. How do I marry between the two? How can I get the best of both worlds, basically? And that's going to be the topic of the next two slides. So the first approach is what I call a migration strategy. And a migration strategy, we're not going to take the best of both worlds, but we can get some of the benefits of the NoSQL movement injected into our existing relational model. One option is something that is called second-level cache in Hibernate, which basically means that for read-mostly application, for repeatable reads, we can actually cache some of the queries in the distributed data model. And in that case, we can save some of the load on our database and basically buffer some of the load on our database. So that would be approach number one. It's very simple. It's very seamless. We're still hitting the database quite a bit, but we can save some of the load on the database, and that might be one of the approaches to reduce the actual hit and embed some of the NoSQL alternatives at that layer. Obviously, again, the value that we'll get to that is not that high. The other example is doing something that will require a change in our code. So in this case, if this is our application, we'll actually change the data model into, for example, a NoSQL alternative or an in-memory alternative like a data grid, but we'll push all the mapping to the database in a right-behind kind of model. That means that the database that we used to work with remains the same. The schema of the database, the data model, and everything remains the same. We at least minimize the change to an area where it really needs to happen, which is the high-performance part of our application. And in that case, we can get much better performance both on reads and on writes. And we're less limited on the database. Obviously, that link here could lead to a bottleneck at some point, but it does push the limit quite significantly. So in many cases, even applying that approach will buy us, the next year of the question. Okay, so the other approach is what I call a mapping strategy. A mapping strategy really means, like in Hibernate, we're mapping between object model and a relational model. In this case, we want to map between a relational model and not an object model and a relational model, but a relational model to a distributed model. The first example that I use here is actually used by Google. So in Google itself, what happened is that we have an application, and Google has its big table that is a key value store, and they're using a data nucleus that is actually used as a mapping layer between the actual client and the underlying storage itself. Now, the benefit of that is that we actually get best of both worlds in this case. We're still using a NoSQL alternative, but we're using an SQL API to that, and our application is completely abstracted from the fact that we're using a different underlying mechanism. And we can avoid lock-in. The problem with that is that, one, there is a lot of overhead in this layer because it does a lot of the mapping here, and it doesn't take full advantage of the fact that the data is distributed. So a lot of the complex queries will actually need to read all the data into the local memory and actually perform those complex queries here. And there's going to be a lot of limitation on some of the queries, especially transaction support. So it's not going to be fully JPA support, it's going to be partial JPA support. But it's still much better transition than just moving to a complete key value store. The other approach, and that's the approach that we're taking here, beyond that approach, and that basically means trying to bring the SQL engine, or in this case JPA engine, embedded into our servers. So each of our servers is going to have its own indexing server, and our JPA driver is going to talk to that server in a native format. So all the logic of the matching and queries, including range and others, would happen here. And therefore, we can execute even complex queries very effectively. And the client, basically what the actual driver does is a MapReduce. So basically pass a JPA call into a MapReduce call if it needs to be parallelized. If it doesn't need to be parallelized, meaning that there is a specific key, it will actually map it to a single partition, execute that, and that's pretty much it. So that's, I think, gets me to the last slides. We have a polling question. So while we'll switch to the polling question, I'll try to answer the rest of the questions again, I'll do that from the end. So Monis Iqbal is asking a question: for second-level cache, will Hibernate JPA transition automatically between RDBMS and NoSQL? The answer is yes. As I said, it will be done at a limited scenarios, meaning queries, repeatable queries, where it will actually cache the queries. That's the most common scenarios in which that will happen. And obviously, every time that you do an update, and if you have a lot of updates, that cache is going to be invalidated. And because it's going to be invalidated, if you do have a read-write scenario, it's actually going to lead to a diminishing return, meaning that you're actually going to face performance degradation and not a performance gain. So you do need to be careful when you actually use that. You do need to use it in cases where it's a read mostly and it makes sense to cache the read, and that cache is not going to be invalidated very quickly. Another question that I see here, could any SQL system, oh sorry, I already answered that. Okay, so that I think gets me to the summary. Again, we've seen so far all the alternatives, most of the alternatives, most of the principles. We've gone through what databases and what drives us to that type of new model. I did want to say one thing clear. RDBMS are not going away anytime soon. They're here to stay, but also the Nosql alternatives are here to stay. They're already out there, and they've been running a lot of large-scale systems. Google and Amazon would be one example, but a lot of the financial industry is actually running on that within memory data grid. Nosql do represent a major shift, and the shift is not necessarily about SQL, as the name may suggest. It's about moving from a centralized model to a distributed model. It's moving away from older thoughts to thoughts that take advantage of new resources like memory resources and the fact that we have more network capacity available to us. The other piece here is that Nosql alternatives and the migration between the existing world doesn't have to be that hard. Obviously, over time, it's going to be smoother and smoother in my view. The main change is going to be, regardless of any of the solution, is going to be, as I said earlier, between a distributed model and a centralized model, regardless of any solution. So I do expect that anyone who has a centralized data model will need to go through a change, and that change is going to be inevitable. We can just minimize that change, and we can minimize the level of locking once we select one of the solutions. So with that, I think I'll just wrap up with some of the other questions that I see here, and then we'll end. So I do see a question here from Mark Wender. How do we handle sync back from in-memory tables back to the local file system? Do you use traditional tools to handle the replication? What we use is our own replication. We call it Mirror. The Mirror service is a service that is actually running in a different process, usually closer to a database. It listens to all the updates, and it opens up a replication channel with the data grid in this case, and when it gets the updates, it actually pulls those updates into the data itself. The other one is by for second level, I think I answered that question as well. So I think can you provide an example of a Hibernate configuration mapping, which has some mapping for RDBMS databases and some for key value store? Yes, definitely. Just do a search on Hibernate and gigaspaces, and you'll find that Hibernate second level cache gigaspaces. You'll find a link to that in our wiki. Are there any other questions? So I would like to thank everyone for participating and for all those very good questions. And hopefully everything is recorded here, so hopefully we'll be able to get that. David, we can touch base offline if you want, and I can give you some more updates about some of the questions that you asked here that I didn't really answer. So thank you all for that, for the question, for participation and listening from the entire hour.
This is Matt from D-Zone again. I would like to thank Nadi for the great technical content that he gave during the presentation, and I hope that everyone enjoyed it, and we really appreciate everyone coming out this afternoon and attending the presentation and finding out more on NoSQL. If you have any questions at all for Nadi after the presentation, feel free to email webinar@gigaspaces.com, and we'll put that in the chat as well so that you can just copy it into your email. And Nadi will try to get back to you as soon as possible with the answers to your questions. So again, thank you everyone for coming, and if you have any questions, let us know. And again, thank you to Nadi and Alit for giving the presentation. Thank you, and have a good afternoon.
Thank you very much.
Thank you.